the end of part 3, and I've got part 4 here, and actually even part 5 to hand out to you. But chemistry in context is trying to give you a little bit of chemistry in the context of how things work. One of the things we'll be talking more about are chemical reactions. So we're going to have to talk a little bit about chemical reactions now. There's different types of chemical reactions. You know that a chemical reaction has occurred if you have new stuff on the other side. So for instance, if I do a reaction arrow like this, I can put R and P. What does R stand for? As I have it listed there. It's a reactant. That's a reactant. Yep. That's what you start with. It's a chemical reaction. That's what you start with. And what does P stand for? Product. What you end with. Yep. Oops. And. Gosh. Goodness. Feels like a Monday. Now, there's different types of chemical reactions, but you know if you have something that new in the end than what you started with, a chemical reaction has happened. So this sort of chemical reaction is a redox reaction. And we already talked a little bit about this on Friday, that in a redox reaction, something has given up electrons and something is taking in electrons. And we're going to look at a redox reaction here in a minute. But at the crux of understanding or tracking this sort of chemical reaction, you need to be able to, for all the atoms, go and identify an oxidation number. And that's actually the next task we're going to do. Before we go on to that, I want to highlight this one right here. It works real good. If you have an Na plus 1, oxidation state is plus 1. If you have an O2 minus, oxidation number, oxidation state is 2 minus or negative 2. But the problem is, or it's not really a problem, it only applies for ionic compounds. Now remind me, ionic compounds, let me pull up I tried to draw the jag in better, but ionic compounds, here's your choices. Is an ionic compound a metal and a metal? Is it a non-metal and a non-metal? Or is an ionic compound a metal and a non-metal? A, B, or C? C, exactly. So ionic compounds will have a metal and a non-metal, ionic compounds. So I just emphasize that. So you have a metal and a non-metal. Because here in a minute when I show you these, you're going to be thinking, oh, dang, I'll assume it's a cation. I'm going to go look, for instance, or it's a metal cation. I'm going to go look at what its charge is up here, and I'm going to give that its oxidation number. No, that's not how it works. That's how it works if it's an ionic compound. Here's what I mean. Let's do these together, if that's okay. Okay. Notice that on the sheet you guys have, I think I must have messed up the instructions. I just copied and pasted. See, I have a sheet that you have. So instead of providing the charges, we're supposed to knock out the oxidation states. Okay, so there's that little N up there. Denote the oxidation states of all the atoms. So you guys can kind of flip back and forth between the previous slide and this slide. It goes something like this. I'm going to pick on the first one, the P2O5. First off, is that an ionic compound? Find phosphorus and oxygen on the ground here. No, there's no metal there. Oxygen and phosphorus are both nonmetals. That's a molecular compound, so we can't use the ionic charges. On the previous slide, what did I tell you oxygen almost is always going to be? What's its oxidation number?
2.
Very -2. Yep, oxidation number is -2, almost always. So I'm going to put a -2 above my 5. Goodness. Put a -2. Ugh. -2. There we go. I'm going to put a -2 above my oxygens. So according to this formula, I have 5 oxygens. So I'm going to start that way. I'm going to say I have 5 oxygens. They are each worth -2. Okay. Now, how many phosphoruses do I have? I have 2 phosphoruses, so I'm going to go ahead and do it this way, I think. I'm going to say plus 2 phosphoruses. I'm going to put a question mark over the oxidation state for phosphorus. I can't use it as in, like, an anion, because it's not an anion. It's a molecular compound. Question mark. So I have 2 question mark. So I'm going to put question mark next to my 2. Whatever oxidation state that is. And I'll remind you that one of the rules is that if you have a neutral compound like this, it has to add up to be equal to 0. All right, so what is my question mark?
So pretty much just oxide.
What's that?
We have to pretty much do the equation to find question.
I think you have to do the equation. I'm thinking of plus 5. Plus 5, this one's kind of symmetrical, feels like to me. But if I make this a plus 5, that makes it a true statement. So the oxidation state of both of those phosphoruses is plus 5. What do you think, Glenn? Does that work for you? Okay. Let's go on to the next one. Now, one of those rules, I said if an element is in its, isn't combined with anything else, like Cl, this is what, 2Cl, so what does that look like? That looks like this. It's adorable. That's it, where there's a bond between those 2 chlorines, that's Cl2. So if you have something like this, it's in its neutral, uncombined form, what do you think? What did I say the oxidation state is? It's 0. If the oxidation state is 0, if it's like not combined with anything else, just by itself, it's 0. And if it has no charge, it's 0. I'll put a 0 there. Yep, that's it. Well, the rule I just told you, what is Zn? It's also 0. Yep, it is also 0. Something that's not combined with anything else, just by itself. Now, in the case of Cl2, it's combined with another 2 Cls were combined, but they weren't combined with anything different. Okay. Well, let's go down to D, and we're going to do D sort of like we did A. So D sort of like we did A. So we're going to go backwards. I'm going to put a question mark over the C. I don't know, because carbon tends to kind of be a wild child. And I'm going to put a -2 over the oxygen. Let's do what we did before. So I have 2 oxygens, and they are both -2. And how many carbons do I have? Just 1 carbon, and it's a question mark. And since there's no charge, that whole thing needs to be add up to 0. So what is the question mark here? I'm thinking 4 plus 4. Yep. So it's a little bit of it's a math equation thing, but it's also kind of a little bit of a just deducing. All right. SF6. Oh man. Is this an ionic compound? Nope. Because we got sulfur here, fluorine here. I don't have any rule for you there. Well, I wish this one wasn't here. But can you trust me on this one? The fluorines is actually, we're going to go with what it would be if it was an ion. If fluorine was an ion, what charge did you have over there? Do you remember? -1. I'm going to go with -1. There's no other chemist here to argue with me. -1. I'm going to put a question mark over the sulfur. Again, I apologize. This isn't in the rules. But let's go ahead and do what we did before. I got 6 fluorines, and I made them -1. And I have 1 sulfur, and I don't know what charge it is, and it has to be equal to 0. So what is the charge on the sulfur? I say charge, I'm sorry. What's the oxidation state? 6. Yes. Yep, plus 6. That's the oxidation state. Oxidation number. Oxidation state and oxidation number mean the same thing. Right? Crash course. All right. So one of the things we do in this chapter is focus on our cell phones. And an important thing in our cell phones is silicon. So actually, this is something that we talked about on, this is Monday. On Friday, we talked about these redox reactions. And sometimes they're called we can call them actually half reactions. You can isolate what is being oxidized and what's being reduced. In this case, what do you think? Are electrons being generated or electrons being consumed here? Generated, exactly. They're being generated. Now, I look at it like this. Let's go back to, what was the oxidation number of zinc? Just regular old zinc on the previous slide. 0. That's the oxidation number of that metal. I'll put 0. And I'm going to actually up here, let's say it loses, kicks off 1 electron, and this makes this a +1. What would be the oxidation state of that if it was a +1? Sounds redundant, doesn't it? Oxidation state would be +1. An easy way, I think, to think of oxidation is if it increases its oxidation number. So what we're saying is, I'm going to put the word start next to my M, and I'm going to put the word end next to my M +1. So this is what you start with, that's your reactant. This is what you end with, that's your product. Do you see where the oxidation number went from 0 to +1? We call that oxidation. Picked off an electron. Well, let's look at this. I'm going to clear my slide because it looks pretty messy there. So then next that we're going to do, I'll try to clear my slide, is to go ahead and assign oxidation numbers to everything. The Al, the O2, the Al, the O, and the Al and the O. Notice that this is what you start with, this is what you end with. All right, so what's the oxidation number? Forget the 4 for now. What's the oxidation number for the Al? 0. What is the oxidation number for each of those oxygens in O2? It's kind of like Cl2. They are each 0, yep, because they're not combined with anything else. So finally I get, is Al2O3, is that an ionic compound or a molecular compound? Find aluminum. Is aluminum a metal or a non-metal? It is a metal. Aluminum's a metal. It joins these guys. So since it's a metal, actually now finally we have an ionic compound. The other day, what number did I have you put on top of aluminum, gallium, indium, and thallium? What cation does it form? You had +1, +2, +3. In this case, aluminum oxide is the name of the Al2O3. Aluminum is actually a +3. That's the charge. Actually, we could have gotten it the other way too, but that's a +3. If oxygen forms an anion, what for this column here, oxygen, sulfur, selenium, tellurium, what number did you put up there? What charge does it form? -2. Yep. I'm sorry, what?
I said, when did we do that?
It might have been the day we were here, I don't know. Yeah, but we put the +1 here, and that was the whole column. And it's 2 here, and then just beginning with the metals, +3. And then over here, a -1, column. -2, -3 row column. Yep. All right. So what is being, look at aluminum or oxygen, those are your choices. So what is increasing in this oxidation number? Aluminum, yeah, it's going from 0 to +3. What about oxygen? It's going down, it's being what we call reduced. Yeah, oxygen is going down. Okay. Aluminum is giving up electrons, oxygen is taking in electrons. Let's get to the other side. Or when you compare the left to right. That's a redox reaction. That's how you identify it. All right. Very good. Okay, so here we go. Second half of the slide. What do you think? In this case, is electrons being consumed or is electrons being produced? Here's my electrons. Are they being consumed or produced? They're being consumed. Yep. Yeah. Something takes in electrons, it's going to be reduced. So again, if I kind of do a similar thing I did before, if this is something like, well, it won't be zinc, but if this is something like oxygen, like O2, what's the oxidation state? It is 0. Yep. Let's just say it takes in this case, oxygen likes to form a -2 charge. Let's say it takes in 2 electrons. Okay, it forms a -2. Okay, and actually the charge of it then is its oxidation state. So we say something is reduced if it steps down in its oxidation state or steps down in its oxidation number. So clearly it's a decrease from 0 to -2, it's stepping down. We say that thing is being reduced. So let's kind of do what we did up here with this guy up here. SiO2, those are both nonmetals, so we're going to have to kind of deduce what silicon is. So what is oxygen, did I say? You can kind of hang your hat on. It's a -2. So if we have 2 -2s, what is the oxidation number of the Si? It is a +4. Does that make sense? Because this whole thing has to be 0, and I've got 2 of those. How about carbon there? Carbon in its uncombined elemental form, what do you think? It's a 0. Yep. I'm going to put a 0 over the carbon. They are so loud over there. I can shut the door, but it's coming from the other side of that door. Okay, let's go over here. Again, just ignore that 2 for now. We need to do carbon and oxygen. So what's the oxygen? -2, so we have to deduce then what the carbon is. 1 oxygen, -2, so what's that carbon? It is a +2, yep. Just simply a +2. That has to be equal to 0. And how about silicon over here? This guy. It's 0. Yep, very good. And in my general chemistry, then I kind of do this sort of thing. Redox reactions are so pretty because something's going to go up in its number and something's going to go down in its number. So let's pair them up. I'm going to pick on silicon. I'm going to find the silicon atom over here, and I'm going to draw an arrow to where it is over there in the product side. So it went from a +4 to a 0. +4 to a 0. Stepping down, so was that oxidation or reduction? Reduction. It's stepping down. It's stepping down. If it's going down, it's being reduced. And to me, you have to kind of pick apart a thing like this before you can kind of see if something's stepping down like that. Yep. So it's being reduced from a +4, and literally it's kicking off 4 electrons to become a 0. Nothing, it's a 0. So then above that arrow, sometimes I'll do RED for reduced. Well, if that's being reduced, something has to be oxidized. So let's look at the carbon. I think that's a good place to turn our attention. Carbon is going from a 0 to a +2. 0 to a +2, so it's stepping up. So is that oxidation or reduction? That's oxidation, so OXID, oxidation. So what this slide does is to pick out what we call the reduction half reaction in the first one and the oxidation half reduction in the other one. All these two things do, this right here, these are called half reactions. That's a half reaction and that's a half reaction. Just kind of pick out their favorite part. Okay. On to part 4, smiley face, note to self. So what was I saying? Oh, I know. I don't do it very regularly, but I gotta get out my Wii U Fit every once in a while. And my trainer told me to smile through anything. I know, right? She did. She's like, you should smile and make your training go better. But I also had a friend, place I worked before, that said, you know, sense of humor can go a long ways too. All right, so we're going to pick up where we left off. All of this was to kind of bring you up to, you know, grab your cell phone, hug your cell phone. It definitely has its fair share of silicon in it. And we're going to talk about how pure that silicon needs to be in order for our cell phones to work. So silicon is actually obtained oftentimes through just sand. So we're going to see some pictures and maybe even a video of how we can turn sand into silicon, a major element of glass. But before we do that, let's look at the chemistry in context. So here we have silicon. What does the S stand for, you guys? What's that S next to the Si? What does the G next to the HCl? You wouldn't want to breathe it. It's a gas. Yep, G is gas, so what's S? Solid, yep, you got it. So this is a gas, and this is a solid. Cool. So we have a solid and a gas yielding a gas and a gas. What do you think that 300 degrees Celsius is? How hot you have to have it. It's like a little recipe. That's wonderful. It is. Just for kicks, because we're on a roll. What is the oxidation number of Si? 0. Very good. And for the next one, do you remember a few slides ago, what is hydrogen usually? What's its oxidation usually number? It's usually +1. I'll go with +1 there. If it's a +1, what's that Cl? -1. On the product side, let's start with the easy one. For the hydrogen over here, what's the oxidation state of that? I'm going with 0. So already you see that hydrogen is what? Okay, hydrogen's going from +1 to 0. Oxidation or reduction? If the number's stepping down, it's reduction. If the number's stepping up, it's oxidation. Reduction, yep. So silicon must be, that's reduction, silicon must be oxidized. Let's pick on this one, we can do this. Hydrogen, you told me, is +1. Let's go with chlorines for what it usually forms if it is in an ionic compound. What number, find chlorine on your periodic table, what number's at the top there? -1. So put a -1 there. I'm not going to write the math out, but we have what? -1 times 3, so it's -3, +1, that gives me what? A -3 + 1, a -2, right? Okay, so if this is a -2, what's my silicon?
2.
+2. So here we have silicon So silicon is going from a 0 to a +2. Is that reduction or oxidation? Oxidation, yep, OXID. And hydrogen's going from a +1 to a 0, so oxidation reduction. Reduction. One of the things I do with my Chem 2 students is, if you find two things that are being oxidized, something's wrong. So anyway, let's take a quick look at this. Now this is a lot of what happens. Do you see where this, which is produced, is further than reacted to give us silicon in its pure state? So actually, no, I think we've done enough of those. It's a redox reaction, trust me. Well, you can tell it's a redox reaction because oxidation state here is 0, and here it's not 0. Wow, what do you think? 1,150 degrees Celsius. That's pretty hot. So I mentioned the purity of silicon needs to be right there for, depending on what you're going to use it in. So with regard to manufacturing, they talk about these 12 N's, not to be confused with normality. 12 N's just means that actually there are 12 nines, N is 9, 12 nines, so 99 point, and then what, 10 more nines after that, % pure. Ah, see, I did, so we did this one together, so just do step 2, I'll give you a minute. So it is remember you guys are getting points for being here, so go ahead and knock out what we've been doing. Just do your best, we'll do it together in a minute, you can do it. Knock out the oxidation numbers, oxidation states for everything there. Sure. Note that we did this guy before. Ooh, silicon. Interesting. Is that what you got? That's hard to read. Two classes in one room. I didn't think of, I wonder if it's just me, but yeah.
History class.
I wonder if they're hearing something. It's a little off.
What do you have above silicon on the left side?
I have this is 0.
No,
This is +4.
on the other side of the equation.
Minus 2. Or +2, excuse me, +2.
Oh, no.
This one's +2 because the hydrogens are -3, and there's 3 of them. So that gives us, oh gosh. The chlorines are -1. Chlorines are -1, and there's 3 of them. It makes them -3, and then the hydrogen is a +1. So instead of -3, that's -2. That's how I think of it. This has to be a +2 to make that neutral. Now this is a good example of, if I were to ask you what's being oxidized, what would you tell me? I'll give you a hint. Yep, it's not the hydrogen or the chlorine, because they are the same oxidation states on the side. The silicon is being oxidized as it goes from this one to this one, right? But check this out. What's being reduced? The silicon. Silicon's going from a +2 to a 0 right here. And it happens in redox reactions. Actually, the silicon is being oxidized and reduced. Welcome to my lab. I have some videos for you. You ready? I've watched videos for a while. Well, before I do the video, check this out. Now I was like, I read this, like, really, how does this work? So tennis balls, I can picture a tennis ball. But what it's telling you is that if you have tennis balls and you have, kind of think of the diameter of a tennis ball, and you have them like 170, there's only 1, 2, 3, 4, there's only 5 here. But if you had 170 tennis balls lined up in a row, and then you were to stack those tennis balls end to end to end to end to end, tennis balls, and then stack them to get from the Earth to the moon. Oh, I can think of a sheet basically of tennis balls. What that's saying is if you have 12 nines or 12 end, then one of those is wrong. So that's the error in 12 nines.
What? But that is totally.
I know. It's weird. It's like, okay, so for whatever reason, I can picture, this is 5 tennis balls. Okay, 5 tennis balls. Okay, so picture not 5, but 10 tennis balls. I don't know what kind of line that would look like, but not 10 tennis balls, but picture 170 tennis balls. And go ahead, and I don't know how you do this, but go ahead and, because they wouldn't stay, right? It's a weird analogy, but if you were to be able to stack tennis balls on tennis balls, okay, and to stack them so that actually your sheet of tennis balls basically reached from the Earth to the moon. So you have a sheet of tennis balls. One of those.
So it's like line of tennis balls.
What's
So
that?
it only takes 170 tennis balls to get to Earth.
No, that's written weird on your slide, which would be 170 stacks of yellow tennis.
Yeah, stack 170. Well, this is the publisher's, but yeah. Some of those publishers, some of them are mine, but stack 170 yellow tennis balls. Yeah, it is weird, I agree. But to me, that's what they're saying. So you have 170 tennis balls. Because, my gosh, I can picture tennis balls and pick 170, I don't think they're going to reach the moon. What they're saying is if you have that many stacks. So that 170 stack, okay, that's it.
And then you stretch them out into one big one.
Yeah, it'd be one wall of tennis balls. Yeah.
Okay.
I don't know.
Whatever.
Somebody thought way too hard about that. So let's watch this video. See what we think. So of course, which one would be more pure, the 5N or the 12N? The 12N, yeah. Which one costs more? 12N. Mm-hmm. So this is kind of talking you through the whole making a wafer. Okay. I don't know. And then you saw them imprint the wafer, and then they took a little tiny chip out of the wafer.
They skip a lot of steps because it says hundreds of processing steps.
They did skip a lot of steps, I agree. I think I have one more video to show you. So, so the word you're looking for, I actually have a word I took out, clean rooms. Technicians work inside clean rooms.
I've been wearing one of them static coats before.
You've worn one of those static?
Wherever you move, if you lift your arm or something, it'll stick to your side when it pulls it up.
Oh, really?
No matter if you put your hands in your pocket, it'll get stuck over. Weird.
With the static
Static coat.
coats?
Why'd you have to learn?
I was working in a drug company. Everybody, because law school.
Was it a, one thing I thought I've heard about clean rooms is they have this positive pressure, so when you open the door, there's air going out. Does that,
Oh, I was like animal drugs and stuff.
animal drugs?
Cool.
Cool. Sounds interesting. I have another video. Let's see if this will work for us. But they're small, those little processing chips. So words to fill in look like this. Okay. I'm not sure. Let's watch the video. They're small. Or do you guys need to fill in those water droplets, mold spores, human hair fibers, beach sand, thickness of a cornea. See, now I'm good with this list, and again, I don't mean to complain against the slides that I've been given to use with this class, but they get smaller and smaller. So thickness of a human cornea, that is very thin. Diameter of a pinhead, the head of a pin, very small. But then the diameter of a pupil isn't either are pupil, right? And they change, depending on the light's coming in. That's pretty big. Do you know what I'm saying? I feel like G is out of the pattern. Unless I'm
The pupil's black part for that, that's a big thing.
Yeah, but it expands less wide.
Yeah, it depends on how the light's coming in.
Does it mean?
And then that's another good point. Why would you use something that's variable? Anyway, let's watch this video. What's that?
So are they talking about whenever there's no light or whenever it's full light?
Yeah. When there's full light, they're very small.
Or a human pupil or no?
That's true. All right. Well, hopefully this is a little more interesting. Let's check out this video. Too many playing.